So, well, good evening and welcome everybody to tonight's meeting. I really hope that everybody's continuing to manage at least kind of okay in what seems to be a continuing and somewhat weird world just now. But, you know, as so often, the night sky has managed to throw up some wonders for us. And in particular, this the opposition of Mars has just been fantastic. And although the cloud cover has been really awful this month, it has been a beautiful sight. And I hope lots of people got a chance to get a decent view. Speaking of the sky, Jim Barber has continued to do our sky notes. And these are on the Society website, along with Ken Kennedy's lunar notes for the month. As well as doing this, Jim has again been working on our next Society newsletter. So if anybody would like to send in anything for the next newsletter, if you send it along to either Jim or to myself, that would be great. It is also especially pleasing and very welcome to see our winter series of talks up and actually running successfully. And so once again, my thanks to David Petersen and to Graham McAteer for organising this for us. While we still can't actually meet up, it's a huge plus to have access to our wonderful speakers who bring us the opportunity, you know, to look at astonishing research developments and current thinking in astronomy. All of our guest talks, by the way, are recorded live for YouTube. And so for anyone who hasn't been able to join in our previous talk live, you can catch up with it on YouTube channel or review anything that you want to see again. So it's my great pleasure to introduce tonight's guest speaker, who is Michael Petersen from the Royal Observatory in Edinburgh. Michael tells me that he grew up in mid-America, then moved off to Massachusetts, where he did his PhD. And since May 2019 is working as a postdoc associate at the Royal Observatory in Edinburgh, which he says is really good and he really enjoys it here. So tonight, I think we are going to be taken beyond the gravitational formulations of Newton to much more complex systems. So over to Michael to tell us, how do astronomers model gravity? And in order to get an answer to this, I shall hand back to David, who will link Michael in and we can catch up later on.
Right, it's all set.
Okay.
Yeah.
All right.
Excellent, David.
So I hope everyone can see my slides and hear me all right. Thank you, June, for that very kind introduction. I'm very happy to be here with you tonight to get a chance to talk to you and, at least in this case, see something that is never affected by clouds, which is computer simulations. Tonight, I'm just going to talk a little bit about demystifying some tools that are changing our ability to study the Milky Way. So my research is fundamentally studying simulated Milky Ways to try and make sense of the complex physical processes that are taking place in our galaxy and try to expand that and see what we can learn about gravity in general and a bunch of other things that we'll see along the way. So the title of the talk is How Do Astronomers Model Gravity? And I'm hoping by the end of the talk, you'll have a bit finer appreciation of what it means when people explain that they have a new simulation and what exactly they've been doing to show you that. As was said before, I'm at the Institute for Astronomy at the Royal Observatory in Edinburgh, which is part of the University of Edinburgh, and I'm very thankful for their support in all of my research that's happening right now. For a little bit of a map of the talk here, I've divided it into 4 different chapters, at which point we'll have little pauses, and we'll explore during this talk, again titled How Do Astronomers Model Gravity? 4 different things. The first chapter is the simplicity of gravity and really looking at Newton's simple ideas for how to define gravity, how to parameterize gravity. And then I'll try and explain why the Milky Way is a key laboratory for studying gravity and what makes making models of the Milky Way such a rich field and why it's something that people have been working on for well over 100 years now. In the third section of the talk, I'll talk about computing revolutions and the things that are leading to our new understanding of how to build Milky Way, model Milky Ways, and what that can actually tell us about gravity. And then in the fourth section, I'll spend just a few minutes talking about what's next and what we can reasonably expect to see in the future, what some goals that modelers have for understanding the Milky Way are, and some technological advances that we might see in the next decade or two. So without further ado, we'll jump right in to chapter 1, the simplicity of gravity. And it really starts, this is a story that starts in the late 17th century with Sir Isaac Newton. He's pictured here at age 46, so 1689, famous painting of him. And what he had written about recently at the point that he's painted here is the theory of gravity, this idea of an unseen influence that has a very simple parameterization, but is a really fundamentally new idea trying to explain the attraction of different bodies that have mass. And he wrote this book. And actually, if you make it down to the Royal Observatory at a time that things are open again, there is a first edition of this book in the Royal Observatory Library. There really is a fantastic piece of really art at this point, and really gorgeous and an excellent window into history. When I promised at the beginning that I would take this simply in gravity, and I just want to lay out some groundwork here about what the problem that we actually need to solve in order to make us a model for the Milky Way and what that actually is. Now, there's no equations in this talk, but I am going to ask you to imagine sort of what the parameters of the equation to describe gravity would be. Gravity is fundamentally what's called an inverse square law. And what that means is that if you look at this, both of the green apples on this slide are pulling on the red apple. If we call this green apple that's fairly close to the red apple, they say that it's exerting some gravitational pull on it. Because gravity is an inverse square law, if you compare the pull of the other apple, it's twice as far away, but it exerts 4 times less pull. But what you have to remember from this is actually the fundamental idea that both of the green apples are pulling on the red apple. Newton was able to formulate this very simply for the solar system. And the reason that you can do that is because the solar system has some very tractable numbers. So his idea, of course, and these are some fairly famous images that I particularly like that hopefully you've seen before. There's the photo of Earth from Apollo 11. There's a photo of that's titled Pale Blue Dot from Voyager 1 that turned around and took a snapshot of Earth, and you can see this small dot here that the arrow is pointing at that is actually Earth. And then a snapshot from the sun from actually earlier this week from the Solar Dynamics Observatory. And in the simplest case where you're trying to you're Newton in this scenario, and you're trying to parameterize gravity, you can write down the equations that will govern Earth going around the sun. And that's because the solar system's numbers, while they seem large, are fairly tractable. So we only have one sun. We only have one star in our solar system. There's 8 planets. There are lots of minor bodies that you've probably heard of before, asteroids and other things. But the scale of the solar system is fairly small by astronomical standards, of course. So we're talking about a little over 1,000th of a light year across. And if you translate that out into numbers that maybe make a little bit more sense, that's 14 light hours to go from end to end in the solar system. Now, these aren't any sort of numbers that there's going to be a test on, but they are important to sort of get the scale that by astronomical standards, the solar system is fairly simple. You have 8 planets and a lot of minor bodies that are orbiting around a sun. And so in that sense, Newton's formulation of gravity is very tractable and fairly easy to understand. However, Newton had already noticed at this point that there was going to be something of a problem in terms of understanding this. So in his book, he had written that the orbit of any planet not only does it depend on something like the sun, but it depends on the combined motion of all the other planets and the back reaction of all of these. So everything in the solar system is pulling on everything else. And Newton actually continued on in this quote to say that he thought it would take the entirety of the human intellect to try and compute all of the forces that were at work in gravity just in the solar system. So to try and put that a little bit pictographically here, the explanation is that all of the apples, instead of having one red and two green apples, we now have many green apples, and all of those are pulling on this red apple. But it's actually worse than that in terms of trying to compute gravity and measure gravity, or to measure gravity with a computer, because all of the green apples are pulling on all of the other apples. So in astronomy terms or in mathematical terms, we would say that there's apples times apples, or apples squared number of steps to compute. So each one of these apples is pulling on every other apple. So if I wanted to figure out the gravity at the point of an apple in the upper left corner, I would have to compute the pull from every other apple, and you would have to cycle through all of the apples until you calculated all of the gravity. And this problem was something that Newton immediately realized was going to be very problematic, and it leads and very challenging to solve. And it leads to why something like the Milky Way is only able to be studied roughly now. And the reasons that this is if we try and put these numbers in context in the Milky Way, and here I'm showing you that same image of Earth taken from Apollo 11, and showing you sort of contextually where it lies in a galaxy that's similar to the Milky Way. As you'll see in a few minutes, our photos of the Milky Way don't look anything like this, because we are currently in the Milky Way, sort of in one of these arms, like where I've shown this photo, the photo of Earth. And this is a galaxy, NGC 5754, that we think is fairly similar to our Milky Way in terms of size scale, in terms of mass, in terms of number of arms. This feature at the center that's called a bar. This is a feature that I did my thesis, my PhD thesis work on. And the sun is sort of located, the sun and Earth are sort of located in approximately one of these arms, we think. But the main takeaway that I want to convey when we're looking at this slide is the comparison of the Milky Way by the numbers to the solar system by the numbers. And in the Milky Way, there's 10 billion stars, and they range in size from 10 times smaller than the sun to roughly 100 times bigger, which is a pretty large range when you think about it for a minute. And the Milky Way is 150,000 light years across. So you can contrast that with what we know about the solar system, which has maybe 100 bodies that you have to keep track of, or 100 gravitational items that you have to keep track of, and is fairly small. So it's fairly tractable to think about in terms of size scale, to something like the Milky Way, where there's 10 billion stars. And remembering what I told you on the previous slide, where we were looking at a field of apples, you have to remember that every apple is pulling on every other apple. And so you have to, if you wanted to compute the gravitational pull for every star in the galaxy, you would have to do that 10 billion times 10 billion times. So it'd be 10 billion squared in order to compute this. And those types of numbers, even with the stunning advances in modern computers that we'll talk about, that are actually still remain fairly out of our reach. So that's really the problem statement here, is that gravity is very simple to write down. It's an inverse square law, as we've known since Newton first formulated it over 300 years ago. And we've known in essentially that same amount of time that problems like trying to model the Milky Way were going to be extremely challenging and require vast amounts of computing power. Of course, in the late 1600s, Newton couldn't possibly conceive of an invention in the future such as the computer. So he couldn't imagine how we'd be able to make models of the Milky Way and learn about them in the future. And that's where we're at right now, which brings us to chapter 2, the Milky Way as a key laboratory. Now, again, for a moment, I'm showing you NGC 5754, Again, this is a facsimile of our galaxy. If we could zoom out from our own galaxy and take a look backwards at what we were seeing, we would see something, we think, astronomers think, that looks sort of like this. So the challenge is for us to make a model that looks sort of like this and make it for what we think are the right reasons. The real image of the Milky Way is also gorgeous, but somewhat more anticlimactic. So the current best set of data that we have for the entire Milky Way is being taken by a satellite called the Gaia Satellite, which was put up by the European Space Agency 5 years ago. The Gaia Satellite is still taking data, and there's a very exciting release that you'll hopefully hear some new science from coming in December. Actually, a lot of astronomers are preparing to work with new data that's coming down from this satellite that will give us an even more unprecedented view of the Milky Way. But for now, we have this image that was released in April of 2018. And this is an all sky image. So if you think about the surface of a globe and what would happen if you unwrapped the globe and tried to lay it out on a table, you would see something like this. So you could imagine taking this and instead rewrapping it around the globe, except you're on the inside of the globe looking out. So this is what you would see if there was no Earth in the way. There was no light pollution, so you could perfectly see the night sky. This is exactly what you would see. So this is why I started off by showing you NGC 5754, because astronomers are forced to infer from this picture and all of the data that goes into making this picture what the Milky Way actually looks like, which is yet another challenge in simulating the Milky Way. To give you some bearings on the Milky Way, I'll show you that this is actually centered on the galactic center. So this region, this very bright region that has a dark band running across it, that's the galactic center. It's a dense knot that's full of tens of thousands, if not millions or billions of stars actually, packed into that small little area. And the dark spaces that you see on top of that are actually cosmic dust that's in front of the stars. So the light from some of the stars is being blocked out. The reason that you see a generally bright patch or a brighter patch across the center of this is because this image has been oriented with the galactic disk. So everything that you see slicing across the center of that image is the galactic disk. There are lots of things that you're hopefully noticing in this, and I'm happy to take questions at the end of the talk on specific features here. The Milky Way is something that I particularly love to study and look at the data for. But for now, I'll just mention that there's another prominent feature in here that you may have noticed. And there's actually two of these in the lower right-ish corner. And they are nearby satellite galaxies, the Large and Small Magellanic Clouds. If you've ever had a chance to travel to the southern hemisphere and had clear nights, of course, hopefully you've seen these. They are really gorgeous, stunning sights. A map like this does not do justice to how large these images actually would be on the sky. So if you get a chance to do that, they're really stunning. So the one that I'm pointing at is the Large Magellanic Cloud, and it's what's called a satellite galaxy of the Milky Way. It's a smaller galaxy that is being completely influenced by the pull of the Milky Way. It's in an orbit around the Milky Way, and is actually the focus of some of my current research that I'll have to talk to you about another time. Now that we sort of have our bearings, I want to motivate all the things that we can use the Milky Way to learn about. And building a model for the Milky Way is very important for a huge range of things. And I've just selected 5 here, and I've oriented them thinking from small to larger scales. So the planets are the smallest scales. Eventually, we'd love to have a model for the Milky Way that goes down to even planet scales, because we think that the larger Milky Way environment will actually have an influence on how planets form. Then going out to slightly larger scales, we have stars. We definitely want a model for the Milky Way that can model every star. Again, I said that that's going to be a little bit of a tricky problem, and I'll explain why in more detail when we get to later chapters. If you remember, there's 10 billion stars in the Milky Way, and we think roughly that many planets or so. If you go out to slightly larger scales and look at what collections of stars look like, and remember the picture of NGC 5754 that I was showing before, that's a key hallmark of spiral structure. That's something that we'd like to learn about. Astronomers and dynamicists are not really sure what exactly makes spiral structure. The prominent LMC that we see in the image is part of what are called satellite galaxies, this class of smaller galaxies that are orbiting large galaxies. And those are something that we'd really like to use simulations to learn about. And lastly, this is an entire other talk. I'll hopefully get a chance to speak about it sometime, but also there's the idea of dark matter. Simulations must include dark matter in order to get a model for the Milky Way correct. I'm not really going to talk about that today. This is more about the computational problems and all the steps that have gone forward. But everything that I'm saying to you now goes doubly for including dark matter, and the fact that we now, astronomers now, have a fairly good handle on what's actually happening with dark matter, mostly owing to the inclusion of dark matter in simulations and what we can learn from them. So this is the point where I want to explain, where I hope that the takeaway is that there is a really good reason to build a model for the Milky Way. If you can build a model for the Milky Way that can explain all of these things, then you feel that you have a fairly good understanding of the fundamental physics and try and explain the beauty of the universe from the smaller scales, relatively small scales, of course, this is astronomy, from planets all the way up to the most massive scales and the distribution of dark energy. Now, I might have swept this under the rug by showing you this image of the Milky Way. And what you can't really see in this is that all of these points that are in this are individual stars, or made up of individual stars. So if we zoom into just what is just one pixel on my screen in this image of the Milky Way, you will see this cluster, Messier 4, which maybe you've seen with your, either with the naked eye on a very dark night or with a pair of binoculars. It's just north of the galactic center and is really gorgeous. Of course, we have the benefit of being able to look at Hubble images of this as well. When you look at this by eye, it's really stunning. You can see individual stars, but when you look at it with Hubble, it's absolutely unbelievable, the dense knot of stars that you can see in this. And so encapsulated in one pixel of the Milky Way here, there's a dense cluster of 1 million stars. So in order to try and get the Milky Way right, you have to be able to simulate all of these stars, or to make the most accurate model for the Milky Way, you'd want to be able to simulate all of these stars. Now, it is true that I've preferentially picked a region of the Milky Way that's particularly rich in stars. Most of the sky is not covered in globular clusters like M4, but there are many, many stars, 10 billion or so in the Milky Way that we would need to accurately compute the gravity for if we wanted to make a true to the universe model. M4 is a cluster with a great history. It's been simulated many times on its own, but what had actually happened in between the time from Newton until the early 20th century is there had been lots of analytic work. So in the eras before computers, of course, there's very little chance to be able to compute the gravity of 10 stars on each other, much less the 10 billion stars on each other. And basically by 1920, with the work of this man, James Jeans, astronomers had nearly reached the limits of what could be done with a pencil and paper. Now, Jeans had done some truly remarkable work developing ways to analyze clusters of stars as ensembles and make lots of progress describing the structure of individual clusters of stars. But when you try and extend that analytic work or the pencil and paper work to the full Milky Way, they rapidly break down. And it's hard to make an accurate model to explain the Milky Way. So this is the state of affairs about 100 years ago. And this is where the story starts to get really interesting in terms of being able to model the Milky Way. And that's going to bring us actually to chapter 3. I've titled this chapter computing revolutions, which has to do with the fact that if you look at this figure, which is the only graph that's in this talk, and hopefully not too opaque. What we're showing here is on the horizontal axis as a function of the years here, showing you how many stars the best computers in the world could handle at the time. So on the vertical axis, I'm showing you the number of stars. I have tick marks at 10, 1,000 stars, 100,000 stars, and 10 million stars. And I'm showing you in each year what the state of the art actually was in the field. So what astronomers have been able to simulate in their pursuit of trying to model galaxies. I'm going to walk you through some of this, but I will say that the reason that there are two colors on here is because there's actually two things that have driven models for the Milky Way forward. And I want to emphasize both of them, and I'll try to highlight them as we go through some of the historical developments in the field. So first, I'll point out that the red points are from what are called direct star cluster calculations, where you actually compute the gravity from every star on every other star. You can see that they follow this track, and there are some jumps in it that are owing to some big advancements, and I'll talk about why that is in just a minute. The black points are actually galaxy scale simulations, and those are using computational tricks. So instead of computing the gravity from every point on every other point, you develop more clever algorithms that allow you to push to higher numbers of stars. And those are two fundamental things that astronomers have been working on in tandem over the past 80 years, since the early 1940s, where I'll start this story. And what I'm going to call both of those is that I'll say that the black lines here and the increase is driven by improvements in numerical techniques. So designing better algorithms and doing research on the mathematics of galaxies to try and understand gravity in a more fundamental way and how to simulate that. And the red line is largely driven by increases in computer power. It's the same reason that cell phones get faster and computers get faster every year. That will be reflected, of course, in this figure. And both of these have an important role to play in being able to model the Milky Way. All right, so in the history of doing astronomical calculations, I always like to start out with this place at the same time that James Jeans was finishing up his ideas about how to statistically treat star clusters in pencil and paper. People had started to realize, well, we could actually harness more human power in the ideas of Newton to do calculations, harness more human intellect, do small bits of the calculations, and everyone will do a small part. And then eventually we'll put everything together and compare the answers. And even the Royal Observatory did something like this. So in 1911, this is a picture from the Royal Observatory's archives, where there were women who were hired to do these pencil and paper calculations that would eventually all be put together to make one larger calculation. If you've seen the movie Hidden Figures, it's fairly similar to what was being done there, being done to do some precision measurements in Edinburgh at the Royal Observatory. And I'm going to call this, loosely speaking, a computational power increase, where people had realized we can actually start to use more and more computing power to try and answer these questions. The next jump is what I'm going to call a technological jump, although you can judge for yourself whether this is true technology. And it's this paper that I really love from 1941, November of 1941. It was published in the Astrophysical Journal by a Swedish professor named Erik Holmberg. And you can see, if you get all the way to the end of the paper, it's a very interesting paper, what explains what he actually did in his work. And it's laboratory work where Erik Holmberg realized that because gravity is an inverse square law, you could try and approximate this using something else that's an inverse square law. And he realized that light is also an inverse square law. For example, if you're twice as far away from a light bulb, it appears 4 times as dim, actually. And so he set out in 1941 and had the Luma factory here of Stockholm, you can see in his acknowledgements, manufactured special light bulbs. And what he did is he set up 2 mock galaxies that were each composed of 37 light bulbs that are approximating stars. And he had photo cells that measured how much light each light bulb was taking in, or how much light was being received at each light bulb. And he used that to compute the gravitational force. So he went through a brute force calculation, similar to the figure of how all the apples are pulling on each other apple. And he figured out at each light bulb point, how much pull there was. And he was able to make this beautiful image from 1941 of 2 galaxies that are merging past each other. So in this figure, this is the state of galaxy scale simulations in 1941. So each one of these galaxies is composed of 37 light bulbs, or 37 stars. And he uses the light that's gathered at the position of each light bulb to compute gravity. And what you can see in the top part, it's an early configuration, and several steps later, he would painstakingly move these by hand using the pull of gravity at each point. Painstakingly, he was able to simulate some things that we now see in real images of merging galaxies, such as these arms being scattered at the spiral arms that are being pulled off of the center of the galaxy. In these, you can see that the center of the galaxy, or this light bulb configuration, remains largely intact, but he ends up with these beautiful spiral arms that look sort of like the Milky Way, look sort of like merging galaxies. And this is in November of 1941. So I think of this as a technical upgrade, a very clever thing to do, but it could also be a computational upgrade. But a real bona fide computational upgrade took place in 1952. The building of it was taking place from 1949 to 1952. And it's this computer that's called Maniac. And already from the earliest days of computers, when they took up room sizes and could only do small numbers of calculations, people were already using them to compute things like gravitational pull and the gravitational interaction of many bodies. So 1952 has a computational increase. And then this is just 10 years later. 10 years after that, we've already reached a point where people are actively developing this in the field and publishing on this. And I love things like this. The summary of this describes this paper from 1963, that the computations here, it's called an N body, where N is the number of stars or features that you're able to resolve. And it notes that it's done on a very fast computer from 1963 here. And it's able to compute up to N of 100. So in the previous 1941 image, we saw galaxies, you would represent the Milky Way with just 37 light bulbs. Now in 1963, we're able to reach about 100 bodies, and you no longer need to represent them all with light bulbs. You're able to encode them into computer calculations. Moving forward through history, and there's this constant trade-off of technology, of computational increases and algorithmic development. One algorithm that's very central actually to even modern work now, we're zooming forward basically 20 years from the 60s to the 80s, is this very famous paper, a really important paper in the field of modeling galaxies. You don't have to remember anything about the actual algorithm itself, but to give you an update, of where the field is at right now, and this is in 1986, a new technological trick was developed that allowed for more efficient simulation of gravity. And when you do that, you can go from the images of galaxies that were either 37 light bulbs or 100 stars. You can go up to things that are composed of 64,000 stars. And doing the same sort of calculations that Eric Holmberg did in 1941, where you have 2 interacting galaxies, you can see that you're able to do this with much more precision and many more points that give you more accuracy, and start to explain some of the structures that you're hoping you'd be able to resolve actually in the Milky Way. Now, a lot happened between 1986 and today, but I'm going to go ahead and take some liberties and zoom significantly forward. Taking us to 2020 is a full range of 40 years, essentially almost 40 years of computational power increases. There's a website that you can look at that keeps track of the top 500 computers in the world, and most of them have been used at one point or another to simulate galaxies. So this is a problem that has taken up some time on the most powerful computers in the world. You can see sort of what's happening now. Computers, of course, look totally different than they used to in the 1960s. Here's just a snapshot of what's currently the second most powerful computer in the world, which is hosted in Illinois in the United States. And the most powerful computer in the UK is the 32nd most powerful computer in the world, which is really stunning still. And it's actually run by the United Kingdom Meteorological Office, which I actually did not know until today. We'll have to see if they're interested in letting us run some galaxy simulations on that. Just to give you a benchmark of what some of these numbers mean, I know that there's a lot of numbers on this slide, and that may not mean anything, but to give you a benchmark, this number here that's looking at how many calculations you can do, the 1963 computer was able to do 100,000 calculations per second. This one can do 7,000 trillion calculations per second, which means that this computer is 70 billion times faster, billion with a B, faster than the 1963 computer, which you would think would allow us to move to absolutely perfect Milky Ways. But unfortunately, we're still really not quite there. We're getting much closer, but this is the point where I'll explain to you where we're at currently with the Milky Way. These are two competing simulations. One of the things that's happening right now in models for the Milky Way is that there are various groups that are competing, and that competition is helping to drive a lot of the science forward. But you can see that we've come a very long way from either 37 light bulbs or 100 stars, or even the 64,000 stars from the image from the galaxies in the 1986 paper. Now we're at a place where 10 million is a routine number to be able to simulate, 10 million with an M. And you can see that we're able to resolve things in these simulations that look fairly similar to some of the features that we saw, especially in the NGC 5754 image. And we think, again, that that's fairly similar to what the Milky Way would look like if we look at it face on. These are two simulations that received a decent amount of press coverage, and maybe you've seen these. If you Google them, you'll find great results from both of these groups and many more gorgeous images. This is just to give you a snapshot of what's actually happening, of what the present day galaxies look like. And I'll do sort of a temperature check in a couple slides to explain where we're at and what sort of problems we're able to tackle with these types of galaxies right now. This is not to say that computational increases are the only thing that's pushing us forward. So those were run on some of the most powerful computers in the world, but there's also plenty of room for technical increase. And this is the only spot that I will actually talk about my own research in this talk, but I'm happy to answer any questions on this. So this is a paper that I recently published that's looking at new algorithms to try and simulate the Milky Way. And so the title slide, the title image from this talk and this image on the left here are from a simulation of the Milky Way that I've been working on, that I've published, that is a very pushing the high resolution numbers of modeling the Milky Way. And we think we're doing a pretty good job of actually reproducing what we see in the Milky Way when we compare it with the Gaia satellite. And that's sort of what we're doing in the top panel here. So there's still room for both technical increases, the algorithmic development side, which is what I specialize in, but also the computational side, the building of new and more powerful computers. And that sort of brings us to what we're going to do next, and things, what we're hoping to do next, we being astronomers and algorithm developers, and where we're hoping to go from here. For the most part, all of the simulations that I showed that were run on computers before I was using computers as sort of a catch-all term for CPUs. And you might have heard of these before. They're central processing units. They're the chips that run everything in your desktop computer, in your laptop. Very small versions of these chips are running your phones as well. And these are largely what's driven the advances to this point. But if I'm allowed to show the figure, the same graph one more time, we still have to reach 10 billion, billion with a B on this graph. And the images that I showed you before are really maxing out at around 10 million or 100 million or so if you look at the black X that's in the very upper right corner, showing you sort of where we're at in 2020. Those gorgeous images of the galaxies that I'll of the Milky Way that I'll bring back again in a minute. So we still have to get to 10 billion. So that actually motivates some work that's being done on the computational side that I'm hoping to take advantage of in the near future. You might have heard of these before, graphical processing units. Scientists looked at all of the computational development that's been happening on the engineering and technical side, and realized that these specialized tools, which are mainly giving you the ability to run more and more powerful video games and more and more beautiful art that's taking place in those. But astronomers realized that you could repurpose them for specialized computing. And this is where we're at right now, is Usher is opening a door that's allowing for many more calculations to take place, and going to allow in the next within the next few years, probably 3 to 5 years, a large change in what we're actually able to simulate in galaxies. Looking a little further ahead, you might have heard of this before. There are a few articles that you can find, but in the coming decades, there will be a sea change in technological advancement that's akin to going from the room-size mainframe computers to a cell phone in your pocket that's 1 million times more powerful. And that's called quantum computing. And I'm not sure about this yet, but I think it's worth keeping track of whether new computational tools will allow us astronomers to build the new generation, the next generation of Milky Way models, and make even more gorgeous and physically informative images. So I want to come back, start to wind things down and bring everything back to what we know and what we're hoping to learn about. So I showed you all of these things at the beginning that we were hoping to use the Milky Way to learn about, and the gravitational pull in the Milky Way, things that we'd like to be able to keep track of going from the small to large scales. But what you might have realized over the course of this talk is that I've largely constricted myself to talking about the large scales and the structures of the larger structures of galaxies. And that's more or less where astronomers are at right now. So we can do a good job going from the largest scales, reproducing the structure in dark matter, doing a pretty good job of looking at satellite galaxies and making models for how the Milky Way and the Large Magellanic Cloud, shown in the Milky Way image, can interact. And we're pushing down to spiral structure, trying to really understand what's driving the gravitational pull in spiral structure and causing galaxies like the Milky Way to have these beautiful spiral arms that we see when we compare them to things like NGC 5754. And I would argue that this is roughly where we're at in our ability to simulate Milky Way galaxies. We're at about 100 million stars. We would like to be able to get to 10 billion again, to be able to actually represent individual stars in the Milky Way. And that's why I don't think that we're there yet. We haven't been able to develop models for individual stars pulling on each other, but I think that that's coming in the near future. And after that, we'll be able to develop models for planets and be able to develop single models for the Milky Way that can explain all of these in tandem and look at the interplay of gravity from the smallest scales to the largest scales, because as we've known since Newton's time, even the small scales or the tiniest things have huge pull on the largest things. And if you combine all of them, the gravitational pull cannot actually be ignored. So we ideally would like to push down to all of the smallest scales. I want to highlight again, of course, that the progress that really has been made, I don't want to make it sound like there aren't interesting things that are happening or that this is somehow not where we want to be. there's really amazing science that's coming out of these. And I would encourage you, if you're excited to learn about gravity or learn about models for the Milky Way, to take a look at some of the public material that these two groups have published, the illustrious simulation, and then there's ones called the Latte Simulation, that are simulations that are part of the larger FIRE group. And so you can, you should be able to Google those and find them, and look through galleries of gorgeous simulated galaxies. And of course, the nice part about the simulated galaxies is that we know exactly how they formed, and we can track that over time, and we can measure the gravitational pull, which is something that we can't do in any other galaxy. And it's still a real challenge as we're currently working on it in the Milky Way. So by means of winding down and hoping to make sure that I've conveyed a few ideas about what we're working on and how astronomers actually model gravity, I hope that I've demystified some of the tools that are changing our ability to really make statements about what's happening in the Milky Way and underpin all of those things that you've probably heard in science press releases explaining what we know about gravity in the Milky Way. So here's what we've learned, what I think we've learned so far. Gravity is very easy to write down. We've known that since Newton's time, and we've also known since Newton's time that it's very hard to compute. Once you start to get outside of anything like the solar system, the problem becomes rapidly intractable. But we're sort of pursuing a twofold increase in these. There's both computational advances that have improved the tools that astronomers have for studying gravity. And those are things like ever larger computers and harnessing things like GPUs, the graphical processing units. But technical improvements have also played a huge role in the upscaling. Things like developing an early simulation that uses light bulbs to simulate gravity, or in 1986, developing a new technique that preserves a lot of the accuracy of gravity, but allows you to compute it much faster. And the technical improvements are really the field that I'm working in the most right now, trying to develop further technical improvements to push that number of stars that we can simulate ever higher, trying to get to the threshold where we can simulate each star in the Milky Way individually. And of course, I would be remiss if I didn't point out yet again that the reason that we're trying to do this and why scientists want to do this is because the Milky Way is really a great test site for being able to learn about the universe, from the smallest scales, like planet-sized scales, up to the largest scales, trying to learn about the distribution of dark matter in the universe. So an accurate model for the Milky Way that encompasses all of those would really be a great thing for pushing science forward and helping us to understand the beauty of the universe and how all of the physical processes work together, driven largely by the influence of gravity. So I'll stop there. I'm happy to take some questions. I hope that you've learned something about that demystifies a lot of the tools here. And I'm really happy that I've had a chance to give this talk tonight. So thank you.
Okay, thank you, Mike. And a small smattering of applause there. We've got a couple of questions come in. Yeah, just find my notepad. So we've got a question from Scully about the light bulb model. I must admit I was a bit confused as to how it worked as well. And could you maybe explain how he calculated and worked out the movements, and was it just like brute force and ignorance sort of thing?
It was. So what he did is he had 37 identical stars. So they're a light bulb that was placed on top of a photosensitive cell. So what you had is you have a device that allows you to measure exactly how much light is being taken in at a particular place. And so he would, in a notebook, write down all the light that was being taken in at each point of this 37 light bulb galaxy. And then he would advance them one step. And then he would see how much light was at that new position. Then he would advance them one step and keep doing that. So it's exactly what you're trying to do in a computer, but he had to do it all by hand.
That is quite a challenge to do that, I can imagine. That would not be fun to try and go through that.
Well, before you knew that a computer was going to be able to do it, you didn't really have a choice.
And a related question, considering the amount of time that it must have taken him to do all of that, is how long do your simulations take? Our last speaker was talking about simulations that took months and sometimes years to run. So did you have long run times in your simulations as well?
So for the most part, no, because we're trying to develop technological advancements that don't push out to year scales. Of course, I'm talking about fast simulations, and they take a month or so in this case.
Oh, that's not too bad, yeah. So that's bearable. You're not sick waiting for hours and months and years.
I will say there's nothing more stressful than hitting go on a simulation that you know is going to take a month.
I can imagine, yeah. Another question from Scully is, in a simulation, say, of colliding galaxies, there may be collisions between bodies because of the high velocities and things. Do you have anything to cope with that during your simulations?
So that's a great question. One of the technical shortcuts that's largely taken is to not treat the collisions. And a reason that it's mostly okay to treat collisions is that not treat collisions is that even in models for galaxies, or even in actual galaxies, the stars are still quite far apart. So the odds of a direct collision between stars are fairly low. Mostly what simulations actually need to be able to do is to be able to treat individual binary stars, because more likely what happens is stars will come close together and not collide because it's a very low probability, but they'll start to orbit each other and get trapped. That's somewhere between the spiral structure and individual stars in terms of what we need to be able to simulate. So I'd say that's something that we're looking at in the next decade, trying to resolve.
All right, that's cool. Yeah, yeah. I suppose you don't want to add more complexity, that's for sure.
No, simple is the name of the game here.
And another question from Scully here is, he's a software chap like me, and a question about the precision. How do you cope with the scale of things? Because I know from when I was in games that, even 64-bit or 80-bit floating point,
yep,
you still ran into accuracy problems once you got this scales that you're looking at. So how do you handle those kind of scaling problems?
So this is a technical question, but a good one. So yeah, in part that's why I didn't talk about this, but that's why I brought up the simple size scale of the Milky Way, because as you've sussed out, you're trying to resolve all of these different scales relative to each other. So the short answer is that for the most accurate simulations, you're pushing out to 128-bit floats, where you have to do that. But again, you're talking about vastly increasing the amount of computational power that's required just to move these numbers around. So we try and sneak in at 64-bit, but there you can see that we're at the point with simulations where the seams are really showing in that accuracy. So we're going to have to confront that soon.
Yeah, I can imagine. It's as you add more and more bodies and bigger scales, then you're certainly going to run into that. I have a question from Colin Steele. So in systems like the solar system, there are often Lagrangian arrangements of large bodies and smaller Trojan asteroids and so on. Is there any equivalent in your simulation, again, similar sort of things that appear in the models, or are there simply too many bodies to model that sort of thing?
No, that's actually great. That's a great question too. So the one of the more challenging things that immediately became apparent in simulations was the ability to form what's called the stellar bar in galaxies. So, and actually the physical processes that make the bar, which are resonant interactions, are the same physical processes that make Trojan satellites in the solar system, or even what allows satellites to remain stable at like the Lagrangian points of the Earth and the Moon. So that same processes, the same processes actually play out on the large scales in these simulations. So one way that astronomers very quickly realize that you can check the accuracy of your models is if you're able to resolve those resonances. So if you don't see those structures in your galaxies, you know that you're not reaching high enough resolution. And that's actually something that's only been possible computationally in about the last 15 years, 10 to 15 years. So that was a nice corner that I glossed over in that 1986 to 2020 computational jump.
That's great. Thanks very much. I'm just checking the chat at the moment. I think that's all the questions we have for now. But we had about 23 people on watching the stream, and everybody's been saying thanks very much for a great talk in the chat window as well. And so we've got lots of feedback. Very appreciative. Good. So I'll hand over to June to close up things.
Yeah, many thanks, Michael. That was just a superb talk. Terrific graphics, really easy to follow you through, and actually it was thoroughly enjoyable, which you know, some things may be very interesting and very informative, but slightly brain achy, whereas this was really just a thoroughly enjoyable talk and very informative. Learned a lot. I can't get rid of the light bulbs thing though.
Honestly, that's the whole motivation for me giving this talk. I learned about that simulation, like, oh, this is too good. You have to talk about this.
It is just terrific to have the talks, you know, online like this, and we thank you very much for giving your time and coming to do this, and very much hope actually that we can get you back for some other informative talks, which you obviously have a huge amount of research ongoing. I guess you have time during your month while you're waiting for the results coming out. But it is super because, you know, highlights is not something that life just now is necessarily peppered with. So having these come along is very enjoyable indeed. So thank you very much. I know that the members of the Dundee Astronomical Society would join me in wishing you very well with your research as you progress, and hopefully things work very well for you in the future with this very exciting field. So in the meantime, many thanks to you. For the membership, I look forward to meeting up again. Our next meeting is on the 13th of November, I'm sure I'm right, and that would be just great. So in the meantime, I hope everybody manages to stay well and stay safe. But my thanks again to Michael for really a wonderful talk this evening, and I'll pass us back to David, who can do the sort of shutdown for our system tonight. But thanks to everybody, and enjoy the rest of your evenings and have a really nice weekend.
Thank you.
Okay, that's thank you very much, June. I think that's about it for everyone. And there was one thing that I meant to mention earlier that Graham said, to remind everyone that if you haven't paid your fees, pay your fees. And if you want to order calendars, please let him know when you're paying your fees about calendars as well. So that was the only other thing that came up. But we'll terminate the stream now. And thanks everybody for joining, and thanks for the questions and encouraging comments in the chat window as well. And we'll see you at the next meeting. Thank you very much.
Thanks to everybody.